Swayam Prabha. Digital India. Educated India.
Welcome back. We already did predicate semantics, but there were my focus was mainly on the pedagogy of it, the understanding of it. So, and also a few topics were not covered in the previous sessions. So, we shall do a few things now in this session. It will be the last session of predicate semantics. So, the first thing we are going to do in this session is this. We will sort of survey the entire predicate semantics, how it goes and everything. So, in a sense, this session will be a summary of whatever we did in the previous sessions, one. And the second point is, when we were doing when I was explaining the topics in predicate semantics, the language was sometimes loose and sometimes okay, but definitely the focus was on pedagogy. It was not on the language for expressing, representing each and every step properly. In this session, we are going to concentrate on the language issue, that is, how exactly to represent each and every step of problem solving, whatever you call it. And then we shall solve new problems we did not really solve in previous sessions, and problems we did not really consider, and also will introduce and discuss a few new ideas. For example, we did not talk much about bondage and freedom, but this is a very important idea in predicate calculus. So, we shall talk a bit about it, so that we understand semantics little better. And then the English definite article the, we did not talk about it in the previous sessions. So, these are the notions we are going to cover, and these are the things we are going to do in this session. So, first of all, as I said, we start with bondage and freedom. Intuitively we understand what bondage is and what freedom is. If we look at it, we can see that here in this case, this variable is bound, right. So, there are three occurrences of this variable, 1, 2 and 3, all three are bound. These three variables are bound by this quantifier, that is all, and there are two occurrences of y, and both are bound by this quantifier. Now, what does this mean? Let us roughly say that M stands for man and W stands for woman. If that is the case, then this means, first, for all x such that x is a man, there exists a y. So, the point is, if x is a man, for all x, if x is a man, then there exists a y or some y or at least one y, such that y is a woman and x loves y, which precisely means that every man loves some woman. Now, we can see that this is a statement. What is a statement? Once again, we just get back to the very notion of a statement. A statement has got an entitlement. It is entitled to have a truth value. It is either true or false. Here we have a statement, and We do not know whether it is true or false, but the point is it does have a truth value. And then we shall consider other things. Now, we can intuitively first see how some variable is bound. So, what is bound? A variable, or more precisely an occurrence of a variable is either bound or free. Now, in this case we can see once again x is bound, or in other words all occurrences of x is bound in this, like here also 4 occurrences, here also 4 occurrences, but y is free. Now, what does it mean? It means that for all x, if x is a man, then x is a woman, and I think we need some correction. So, here instead of x, this should be y, and if we correct here also all x's, we just change all x's to y, otherwise it does not make much sense. I made a mistake in typing. Now, the thing is, here we have 1, 2, 3 occurrences of x, and we can see that all 3 are bound, but the occurrence, both the occurrences of y are free. Now, what does it mean? It means that, it roughly means that for all x, if x is a man, then y is a woman and x loves y. Now, y is a woman means nothing, it is neither all nor some. So, the point is here y is unquantified. So, y is free. Now, if just y happens in a structure, in a formula, or if just x happens in a structure, it is neither bound for free or free. For example, we can say that m x, look at the difference between some x m x and just m x. In m x just says that x is a man. What does it mean? There is it means that x is a man, but what is x we do not know. But the second formula says that there exists at least some x, that is, I pick something up and then that thing I pick something. So, there exists at least something which is a man, which means that there is at least one man. So, in the interpretation of this, you can see that there is no x, but in the interpretation of this x must be there, which means that a free variable will never represent a statement. That means this will never have, that is m x will never have a truth value, but some x m x will have a truth value. We can see the same thing here. This means that if everything is a man, then there exists some woman. It is definitely a true statement, very strangely in the framework of logic. This is a true statement because it is vacuously true. Why? Because what is the truth condition for if then? It is basically 1 1 1 1 0 0 0 1 once again 1 and 0 0 1. So, there is only one case of one case of falsity, that is 1 0. In this case, if everything is a man, which is definitely not true, not that everything is a man. So, because this is 0, whatever you do, it will have just one case. So, let it be 1, the truth value will be 1, let it be 0, the truth value will be 0. So, this is called vacuous truth, where the antecedent part of a conditional statement has the truth value 0. So, naturally the sentence receives the truth value truth. So, but we can understand that this is also a statement, and then look at here, this is also a statement. Here all occurrences of look here, this is not a statement, because here there are 3 occurrences of x, 2 are bound, this is bound and this is bound, but this is not bound. That is the reason, once again, when I try to interpret this formula, this x will be occurring free. Because it will be occurring free, the statement will never receive, or it will never have the entitlement to have a truth value. So, what is the summary of it? Bondage guarantees a truth value. If I have bound variables, anything, for example, I can have all x mx or some x wx, which means something, which means that everything is a man or there exists a woman. Both are statements because they are either true or false, like each of those is either true or false, but freedom means the absence of a truth value. So, as we have seen that mx will never have a truth value. In a statement, all variables are bound definitely. That is what we are trying to say. A formula with free variables is not a statement. We are summarizing whatever we said. We need to treat freedom and bondage differently. A quantifier such as all or some binds a variable. In an artificial language, the scope of a quantifier is indicated through bracketing. What is that? We can see that the scope of this quantifier, because of this bracket, so this bracket indicates the very scope of this quantifier. It is from here to there. So, here, so whatever comes within the scope of this will be bound. For example, this occurrence of x. Now, what will be bound? Whichever variable is there in the beginning. So, here this x is bound, this x is bound, and once again this should be y. So, there are two x's within the scope of it, 1 and 2, and we can see that both are bound. And what is the scope of y? Now, this quantifier is binding these two, actually these three, technically speaking, these three occurrences of y, but this is just the binding variable. So, this is to indicate which variable is to be bound, but the most important variables, occurrences of y, are these two. So, once again we can see 1 and 2, and both are bound by this. So, the scope once again is indicated by the scope is once again indicated by a bracket, and in this case we can see in this formula, although this x is bound, this x is bound, this is not bound, this is not bound, and although this y and this y are bound, this occurrence of y is not bound. It is because the bracket is from here to there, then it is outside the bracket. Because this part is outside the bracket, it is not bound by these quantifiers. So, we understand that as far as the artificial language is concerned, binding or rather the scope of a quantifier is represented or is shown through bracketing. What happens in a natural language, or we can talk about natural language after some time. Presently we can talk about just the language, the English like language we are considering, not really English, but the English like language we are considering. Now, in that we compare these two sentences, 1 and 2. Some man loves that man, and some man loves every woman, and some man loves that man, and that man loves every woman. Now, one can be paraphrased as some man loves himself. Now, unfortunately, so far we do not have any tool for writing for representing himself. That is why we just say some man loves that man. So, that man is to repeat. If we remember the formation rules, then we can understand that this is to repeat, and this some man is another some man. Definitely there is no repetition. Had there been repetition, then it would be, as you see in 2, it is some man, that man and that man, which means that they will be co-indexed. But in this case these two are co-indexed. This is a different thing altogether. So this is yeah, and the second one, that is 2, can be paraphrased as some man loves himself and he loves every woman. Now he is a binder. He goes back to this one here. They're all co-indexed. So now we shall see how to treat this in our ordinary in our logical representation. Now because of binding, as we can see that here in a sense some man is the binder, and till here the scope of the binding is there, and this is a completely different scope. That is the reason because of the binding cannot go, the binding cannot cross, and it stops here. Here the binding of some man, or the bondage, if you like, the bondage of some man crosses the boundary of and it reaches there. So we need to understand this happens due to binding. So in the artificial language it's very clear, you can see how the binding happens because of the brackets. In a natural language, binding and freedom are comparatively more difficult. It is because you need to understand that through words. In our English like language, once again this is easier than it is in real language. It is easier because we consistently say all these things, some man loves that man and some man loves every woman. We can understand that. Here the binding gets cut or it gets disconnected, and in the second one some man loves that man and that man, here the binding goes on. Now we can see that these two sentences have very different derivations, and is a very important thing to understand. Now this is one bound statement, and this is another bound statement, and this is a conj, right? It is a conj, means it's a conjunction. We can all the time look back, we can all the time refer to the old rules, the old syntactic rules, and understand what a conj is. A conj is either and or if then, or if and only if and stuff, or not. These are conjues. Now the tree structure of this will be something like this. Here you have some man loves that man, which is bound in itself. What I'm speaking sometimes a little loosely. It is just for the sake of understanding. It is not very technical. Sometimes I have to speak little tightly, but we understand when we switch from a tight version to a loose version. So all I'm trying to say is, here this is bound, and this one bound thing, which is a statement, is on the one hand, and on the other hand you have this thing where you have some man loves every woman. So this is another statement, and here you have and. So this will be computed. We will see the steps of computation. This will be computed through some steps. So basically this will come from V1 loves V1, and the combination, we know the combination rules and stuff. I am not repeating everything, and then this will be derived, and this is a different derivation. This will be derived from V1 loves V2. Now the point is, this V1 and this V1 are not the same thing. So because this is a complete different procedure, these two are different procedures. We could also say that this is V3, but anyway, there is no harm if we call this V1. So the complete truth value of it, 1 or 2 will come here and will come here. some truth value, whatever it might be, and then and will compute that, and we have a whole sentence here. But the second sentence is very different. Why is it different? Here, not that there is one statement here, there is another statement there. No. So, this actually this is derived from a different. So, the underlying structure of this is very important. Let us look at these two sentences and look at the difference between the two. The first one is some man loves that man and some man loves every woman. It sounds very much like some man loves that man and that man loves every woman, but they're completely different. These are two different sentences. In here, basically the derivation starts with an underlying formula, which is something like V1 then loves, then because that man. So, it is once again V1, and I repeat V1 because that man is there, and V1 loves V2. Now, this is a different variable once again. Now, from this we need to calculate the whole thing. We need to compute the whole thing in a step by step manner. We will see the derivation, but the point here is the two ands are doing two different things. Here, this and will compute the whole thing only when we assign truth values to these partial things, to these formulas, and the previous and already had two ready-made truth values. After it gets the truth values, it can work, but in this case the truth value will be assigned to the entire thing, including and, in one go. We shall see how we need to do these things. We just need to revise the semantic rules once. So, this is about about any structure like where we have, if we remember, where we have S goes to NP and VP, or S goes to NP and VI, whichever way you want to read this. You need to see the so basically this is the rule for the 2 plus predicate, and this corresponds to this, and this corresponds to, for example, you have a structure like S goes to NP, and then this has to be VI always, but then here you can have VT and then another NP. So, basically the first rule 1 is about this construction, if we remember, and rule 2, that is this, is about this construction. This is common to all sentences, because finally this, that is NP, the NP will not somehow unite with any VT. It will unite directly with the VI, if we remember, which is something like not loves but loves John. So, when I have Mary loves John, Mary actually unites with loves John, not with loves. So, what unites with loves is John, not Mary. So, the structure once again. So, S goes to NP, or in this in the version of this logic just N. So, S goes to N and VI, VI goes to VT and N, and then what is this VT? The last thing of VT is the terminal node of VT is loves, and the terminal node for N is here, in this case John. So, John and loves unite, and here this is already loves John, and this goes to Mary. So, loves John and Mary come together to make Mary loves John. So, so that's why we have these two rules, and then we have rules for negation and all that stuff. If we remember, then it's very easy for us. So then these are the conj rules, and we go to this is the most important. These are the most important rules for us, these three, and we if we didn't have time for discussing this one, that is rule 7. In this session we are actually going to deal with rule 7. So, but these we already remember. So, this is for all, and this is for some. So, yeah, just it's a quick reference to the rules. We need to refer back to the rules. Now, yes, we get back to the first sentence, which was some man loves that man, and some man loves every woman, and we can 1 and 2, and they are glued by this conj. So, that is the reason we need to compute these two statements separately. So, first we are doing this one, which is actually this statement, and secondly we will do this one. Now, the first part, which is some man loves that man, derives from V 1 loves V 1, because some man loves that man. If you remember the syntactic rule, the relevant syntactic rule, you can see that from this structure the first occurrence of V 1 or the variable must be replaced by some and a common noun. Here in this case it is man, and then every other occurrence of that very variable will be replaced by that the same common noun, in this case man. So, that man. So, I am just once again referring to the rules, but the second one is different. Here you find two different variables. So, there is no repetition. That is the reason you. So, there are different steps of derivation. Now, the first one with 1, that is V 1 loves V 1, we just add man, and following R 6, which is about the existential, and following and then we are doing it, we are applying, we are sort of replacing V 1 by man by following the rule R 6, which is about some. We get some man loves that man. So, the first one is some man and then that man. And what is the truth value of it? So, the truth value computation, some man loves that man with respect to m g is 1 if and only if for some value assignment g e v 1, because here our variable is v 1, such that man with respect to m g it is, we are talking about an e which is taken by man as an argument, and 1 is given, that is it should be a man, that e should be a man. In that case, only in that case it will be this. So, for some value assignment this must be the case. So, I think we as I said, I will not concentrate much on the steps, on the understanding part of it. I assume that we now understand enough of predicate semantics, but here our concern is the language. So, then relevant values, we just get back to the values. We can actually check whether there is some value assignment g e v 1 such that e is a man and v 1 loves v 1 comes true for that assignment. Now, we can roughly see there are two men, that is A s and H k. If you remember, A s is basically Anwar Sadat, I am not writing the full form, and H k is Henry Kissinger. So, there are two men and two women. We just add one woman, say this Kamla for our convenience. So, and let it be, so let the name be Kamala, and let the denotation be Kamala and then Roy, say for example K R. So, this is the short form of Kamala Roy, which is K R. I am just writing the short forms. So, we have two women here in this, that is Liz, if we remember, and Kamala. Liz is basically Queen Elizabeth and Kamala is Kamala Roy. And there are two men, Anwar Sadat, the names are, Anwar Sadat is the real man, if you remember, but the name of Anwar Sadat is Sadi, and the other man is Hank, that is Henry Kissinger. Henry Kissinger is the real man, but Hank is his name. Now, if we look at the structure of loves, we can see that Sadie loves himself, Sadie loves Queen, that is Sadie loves Liz, and Hank loves Kamala, Hank loves himself. So the point is, we should find a man who loves himself. Now we are happy here because Hank is a man then who loves himself. So we are happy with this because there is at least one value assignment, G E V 1. So what is this E? When so if G assigns H k to V 1, then we can see that with respect to that the truth value of this will be 1. Because of that, we can say that the entire sentence will receive the truth value 1, because this is a sum case, which means this is an at least one case. So because at least one satisfies this, we must say that this is perfectly all right. And then we get back to the second part of it, that is this part, some man loves every woman. So is it? So yeah, so that is why some man loves that man is 1, since Sadie is a man who loves himself. Then we go to the second part of the statement, that is some man loves every woman. In this we see that we start here. So that is 2 plus man, we once again apply R6 and we apply that to V1. So this V1 R6 gives it some man loves V2. V2 remains V2 because there is no repetition here. It is just one occurrence of V2, so it remains V2. And we just consider once again, I hope it should go a bit up so that we can see the full form of G. Now what is V2? So G gives HK, that is actually Henry Kissinger, to V2. So what will be the next step? In the first problem we are doing all steps, and in the second and third problem we will not concentrate on each and every step, we'll skip this step, but here we are doing this step. So so now we are here. What is the truth value of some man loves V2? So it is 1 if and only if some man loves Hank, because V2 gets Hank by V2 receives Hank from G, the initial value assignment function, and then some man loves V2 is 1, since Hank is a man and he loves himself. So now some man loves V2 plus then the next step of it, some man loves V2. So I just write 12 here, the number is missing. So some man loves V2 plus woman, and we follow R5, that is we apply R5 to V2. Then we get some man loves every woman. Remember, 5 is the rule for every and 6 is the rule for some. So here is our sentence, some man loves every woman. Now we compute, so this is partial. Why this is partial? Because this includes this one, this thing includes this partial thing. So this is just to show that that by doing this one we are doing a part of this whole thing. So this is just to show the relation between this whole thing and this partial operation, I mean this whole thing and this partial operation. So now we have two different variables. How do we write it? So the language, we have to be very careful about the language, because the textbook doesn't really give us step by step solutions to problems. So I prefer this language. I would say some man loves every woman. What is the truth value? So what is the truth condition? Sorry, some man loves every woman with respect to mg is 1 if and only if for some e such that man takes e and yields 1, and this for is repeated for all f such that woman takes f and gives 1, V1 loves V2. Now here there is a trick. You see, we are considering a G. It is not. It is a G prime. It is a variety of G that 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 assigns E to V1 and F to V2, and E in this case is some and F is all. That is, it is looking for some E which is a man such that all F when F is a woman, every F when F is a woman would be such that V1 would love V2. That so when this is the case, this so once again I am not explaining it because already I did that. I am simply simply showing it. So the language of it, and we can see that some man loves every woman is 0, since there is no man that loves every woman. If we had one man, so we can get back to the values, and you see the structure of love. This is the structure. So yes, Hank loves Kamla, true, but Hank does not love Les, and Sadie loves Les, but Sadie does not love Kamla. So we don't find a single man who loves all women. Therefore the truth value of this is finally, the truth value of this part is 0. Now we remember that on the previous page we saw that this was, the first part was 1. So this part is 1 and this part is 0. So and will compute the truth value of the whole statement, it will be 0, because and what is the matrix of and? It takes 1 1, maps that to 1 1 0, every other thing actually will be 0 0 1 0, definitely 0 0 0. So this is the case of 1 0, so definitely it is going to be 0. So we go to the next example. Sometimes the stylus doesn't work very efficiently. Anyways, as I said, here the derivation starts here, that is V1 loves V1 and V1 loves V2. So there is kind of a repetition, and then we apply rule 6 to V1 and we add man to it, and what is the result? We get this sentence: some man loves that man and that man loves V2. That is the reason, because here you remember that it is a case of binding. So some man, in a sense, not in a very strict language, but in a sense binds both the occurrences of that man, but not V2. V2 is a different variable, it has got a different binding altogether. We will see the binding. Now it is free, now V2 is free, but it will be bound after some time. So then this is the binding for V2. Some man loves that man, that and that man loves every woman is derived from step 2, and then we add woman and we apply rule 5, which is the rule for every to V2, and this is derived, this final form is derived. Now we compute the truth value. So G has gone there, G shouldn't have gone there, but it is a typing problem, I couldn't help it. Anyways, so some man, what is the I am skipping one step, I am skipping this step, I am skipping the truth value computation for 2, I am going to 3 directly. So some man loves that man and that man loves every woman with respect to MG is 1, if and only if for some E such that E is a man, and for all F such that F is a woman, V1 loves V1 and V1 loves V2 with respect to M. This is very, very important. So here it is we are talking about the G which assigns E to V1 and F to V2, but E is a case of some, whereas F is a case of all, because we remember all women, so which means precisely that we need to find at least one man who loves every woman. some man, oh sorry, no, it is a little more complicated. This is there, right? So the truth value of the whole thing should be computed together, not that they are two different things. So some man loves that man and that man loves every woman is 0, since there is no man who loves himself every woman. So of course it is not true that some man loves every woman, but we can change the truth value, not the truth value, the value of loves to make it true. For example, we can see that Sadie loves himself, Sadie is a man, Sadie loves Les. If we just added one pair, that is AS and KR, that sentence would be true. Here is a man who loves himself and who loves every woman. So there are two women, and then that man loves both the women, but unfortunately this is not there. That is why the truth value computation gives us finally 0. And then we go to another case where we are just showing varieties. We go to another case where we have practically 3 different variables. For example, some man hates some woman and that man loves some woman. Now you can see, although these are the same phrase, some woman, they do not mean the same thing, they are different, because once again for binding. So this is one binding, this sum binds this sum binds this, but these are 2 different bindings. If you put it that way, casually speaking, there are 2 different bindings for this, but this some man goes it crosses and it goes after that. So yeah, here is a case of repetition, that is why we have V1 and V1, but these are 2 different things. So we have V2 and we have V3. So now the derivation, the first step, we apply R6 to the variable V1 and we get this: some man hates V2 and that man loves V2. So the first will be some man, this will be V3. Correction once again, this is V3 in the original. Yes. So with the correction, yeah, I made many mistakes while typing, because sometimes I'm very bad, I'm a very bad proofreader, and sometimes all these 1, 2, 3 are very confusing. Okay, so the first derivation is some man hates V2 and that man loves V3. To the same phrase, they are not the same variable. So the second is this some woman, where V2 gets some woman, that is another application of R6, and the third application of R6 will make this some woman. So finally we compute the whole thing together. Here is a slight change we can see. Some man hates some, so we are at step 5. Some man hates some woman and that man loves some woman is 1. What is the truth condition? If and only if for some E such that E is a man, V1 hates V2 with respect to this whole thing, that is M G E V1 F V2 is 1 for some F such that woman is 1. So actually we have 2 things, E and F. So E goes to man and F goes to woman, and then V1 loves V3 with respect to, once again, this complicated thing, that is M G E V1 and H V2. Now the E is the same, because you see that man, so it is some man that man, but here it is F, here it is H, because these 2 have to be different. So that is why it reads once again, some man hates some woman and that man loves some woman. So these are 2 different some woman. M G is 1 if and only if for some E such that E is a man, H1 hates V1 hates V2 with respect to M, G E V1 F V2 is 1 for some f such that f is a woman is 1, that is f is a woman, and V1 loves V3 with respect to M and G. EV1 and HV2 is 1 for some H such that woman, that is that H is a woman. Now, which precisely means that we need to find at least one man who hates some woman and loves some woman, and they need not be the same person. They can be different. Also, they can be the same person. We don't have any problems had it been one person, had it been one woman, but practically it doesn't happen. That is, we cannot both love and hate. Maybe we can, but we assume we can't. But anyways, so now in this case, some man hates some woman and that man loves some woman is 1, since a man called Hank hates Liz and loves Kamla. We get back to the value of loves, and we can see that you see Hank loves Kamla, but also the same person Hank hates Liz, right. So, there is some woman a man hates, the same man also the same man loves some other woman. That is why the computation gives us 1 in this case. So, so once again we just see we concentrate more on the language part of it, not very much the other things. Now, we have the definite article the. Frege in On Sense and Reference would analyze the roughly this way. I am not saying that here I am absolutely technically precise and correct, no, not really, but this is a very rough, very lucid discussion on the topic. We cannot go very deep. So, that is why we just have to put it in a rough manner. Now, in the Frege analysis, roughly, once again loosely speaking, this underlying structure, so this structure, that is X is a man, underlies both John is a man and the President of India is a man. Now, which means that as if one single structure which is like this, like X is a man or MX underlies John is a man and the President of India is a man, as if X could be similarly replaced by both John and the President of India. That is, John is an entity and also the President of India is an entity. They could both replace X and make the statement and make statements like John is a man and the President of India is a man. But this was challenged by Russell, and this paper on denoting, which was published in 1905, actually this paper changed the very understanding of logic. It changed also the way people understood the English language, especially the definite description part, definite description in the sense the so and so. So, Russell, I am not once again I am not talking about Russell's refutation of the Fregean theory, I am rather concentrating on what Russell actually said. Now, Russell would say that the two sentences, that is John is a man and the President of India is a man, would have completely different analysis. So, because John denotes the person John. So, yes, MX, we have MX and X could be directly replaced by John, and we could have John is a man, but the same does not apply to this phrase, the President of India, because the President of India does not really pick up a single denotation so easily, of course, not like what John could do. In fact, it has an incomplete meaning. We will see that. The expression in B, that is the President of India is a man, the expression in B means or just this expression, the President of India, means there is one and only one President of India and something whatever. So, the sentence and B, that is the whole sentence means that there is some individual I who is a president, or who is some president of India. Some is a bad way of putting it, who is a president of India, and for any x, if x is a president of India, then x is identical to I, and I is a man. Now, why is it put in such a complicated manner? It is because I have to ensure a few things here. So, you can see the symbolic representation of it. Now, what does it say? This part, suppose this is not there, let us ignore this. Ignoring this part, the reading of this sentence would be plain and simple. There exists a President of India, and that President of India is a man, which means some President of India or a President of India is a man, but that is not the intention of the main sentence, which is the President of India is a man. So, what do we do about that? We just say that for all x, if x is a President of India, then x is y. We may understand this through a very simple mathematical expression. You can say that the successor of 4 is odd. So, successor of 4, let the successor of 4 be s and let odd be o. How do we write it? We write it like there exists some x such that x is a successor of 4 and that is odd. But then what is this part doing here? We have to add this part now. We have to now say if anything else, or if anything is the successor of 4, then that is identical to this very x, the existing x. For example, 1 plus 4 is definitely the successor of 4. Also 3 plus 2 is the successor of 4. Now, you see they all happen to be 5, they are all identical to 5, or 5 plus 0 is also the successor of 4. So, the point is if anything, so there exists something x which is successor of 4, and then if anything is a successor of 4, like 4 plus 1 or 3 plus 2 or 5 plus 0 or 2.5 plus 2.5, if anything is a successor of 4, that is identical to that existing thing x, which means that this so we just write that for all x, for all y, sorry, x already is taken. If y is a successor of 4, then y is the same as x. Now, this identity is a unity maker. So, if there are 20 such expressions here, for example, it could be anything, it could be 1.5 plus 3.5, it could be anything. All these cases, if this is a successor of 4, then it is identical to an existing thing called x, which means that not only all these things are the successor of 4, also it exists. So, together these two together somehow says that there is one, and so this is the one part. There is one successor of 4, yes, but that is only one successor. There is no other number. So, it is at least and at most one successor of 4, and that successor x is odd. So, this part associated with x is ensuring that x exists, and this part assures that we are talking about a unique x, right. So, this, as I said, this changed the very understanding of logic in the 20th century, in the early 20th century. Now, how did Montague manage this? He managed it this way. He made this rule: if alpha is a Cn, that is a common noun like man, woman, whatever, u is a variable like v1, v2, and phi is a formula containing at least one occurrence of u, then for phi prime, as in syntactic rule 7, which is the rule about the phi prime with respect to mg is 1, if and only if there is exactly one e in A is the set of individuals, if we remember, such that the value of alpha, that is that E is an alpha, alpha is the count noun, and the value of phi with respect to m and g e u is 1. So, we need to understand this phrase, what it is trying to do. So, look here, we consider just one sentence: the man loves Hank. Is it a true statement or not? Of course, it is a statement. Now, what is the derivation? It starts with V1 loves V2, V2 is replaced by Hank, but we are not getting into that. We are starting here, that is V1 loves Hank, and then we just add man to that, and we apply R7, this rule, and we make the man loves Hank. It is true if and only if there is exactly one E such that E is a man and the value of V1 loves Hank is 1. Is it the case? We get back to our old model. Is there a unique man who loves is there a unique man, the man? So, if we go back, yes, there are actually 2 men in our system, that is Sadie and Hank. So, the man in a sense fails in the system, because the man will always give you the truth value 0, because precisely this is saying, this is claiming that there is one and only one man in the system, and that man loves Hank, which is not true. So, that is the reason finally the truth value of this comes to be 0. So, the man loves Hank is 1 if and only if, I just read again, there is exactly one E such that E is a man and that man loves Hank. Because that is not the case, it is 0. So, yeah, as I said, in fact both Hank and Sadie are men. So, in this case D fails, but it could succeed if we have something like the man who loves Hank, because Hank is the only man who loves Hank. So, the man who loves Hank is Hank would be a true sentence, but this is false. So, we stop here, and this is pretty much about predicate semantics. Thank you.